Last class, what we discussed was circular orbits, right? Last class, and parabolic orbits as well. Sorry, elliptical orbits. Let's talk about parabolic orbits a little bit. How do you define the parabola with respect to conic section? Do you remember defining a parabolic conic section? What is it? What is the eccentricity? Look at This is the trajectory equation. Right? Let's substitute it E is equal to 1. You need to know what this E epsilon is. Energy elliptical orbit. Sorry, parabolic orbit. So parabolic orbit. How would a parabolic orbit look like? How does a parabola look like? This is how a parabola looks like. And let's say the orbiting body is here. Here. What is E? Any idea what E is? E is the semi-major axis. What is the semi-major axis of a parabola? How do you define a semi-major axis? Semi-major axis. Uh, you go back and look at your book. A for parabola is A is equal to infinity. Let's call this A. Okay. If epsilon is equal to 0, this V escape is the escape velocity. If you want to escape the orbit of any central body, if you want to escape escape Earth's orbit, you know what escaping is? Huh? Correct. If you want to go to another planet, if you want to go to, let's say, moon, you have to first escape the gravitational pull of Earth. And the least velocity you will need to escape is defined by this. Depending on where you are, the escape velocity should at least be this at that point. Right? You're in a circular orbit, right? You're just cruising along. Let's say you're in this orbit. Okay. This is the elliptical orbit. And you want to escape at this point. Okay. Escape in the sense you want to fire a thruster at this point so that it just gravitational attraction of this central body is no longer a no longer a factor. Okay. So the velocity you need at this point is defined by just figure out what your area is. Okay. Divide the gravitational parameter of this by that this and use this equation to generate that kind of velocity. It's going to escape the gravitational force. And this is how you would approach if you were to go from Earth to moon. You would try to do something like this. If you're trying to do the free-body problem, you would do something like this. Go into a parking lot. Keep on increasing your distance, and at one point you're just going to go to moon. And if you recall, what was V circular? Do you remember what V circular was? Look back into your notes. Say it again. Square root of mu over r, right? So you combine these two, they say V escape equal to root of 2 times or 1.41. So you can get it. Look at it like this. If you want to escape, if you want to launch a satellite which needs to escape the orbit, you would first put it in a circular orbit. Okay? And then you would increase the velocity by what percentage? 41%. Right? So if you increase the velocity by 41%, whatever velocity the satellite is orbiting, okay? Keep this in mind because you will get a question in exam asking you to prove something similar. And say prove that the escape velocity required from a circular orbit is 41% of that velocity. Just keep in mind that parabolic orbits are very interesting orbits. There is something called lost in space model. If you are looking at let's say going to another planet, okay? The first thing you're going to try and do is escape the gravitational pull of Earth, right? And once you escape the gravitational pull of Earth, you want to make sure that you have enough energy left to go to the other planet. And what happens is, if the energy is just enough to escape the gravitational pull of Earth, what's going to happen? You're going to, let's say you're going to be here, okay? Relative to the Earth, you're practically stationary, you're practically there. And you're not in the vicinity or you're not in the reach of any other planet pulled by its gravitational force. And you yourself don't have any energy left, any fuel left to go any further. In that case, you're just stuck there. You are, although you're moving, relative to this body, you're not moving. You're just there. It's like playing catch. The distance you maintain, from the person in front of you is the same. You're never going to catch that person, right? That's something which can happen here. And also this parabolic orbit, this is one of those orbits where you see, you may see like rectilinear motion. You know what rectilinear motion is? Motion in a straight line. For no other orbit you're going to see rectilinear motion, right? You cannot say for an elliptical orbit the motion is rectilinear orbit. Circular you cannot say that. Even hyperbolic orbits you cannot say that. But for this, if you extend this long enough, this is an open orbit. Okay, this is not a closed orbit. I'm talking about not the elliptical orbit. I'm talking about parabolic orbits. Parabolic orbits are open orbits. So this thing will never close. Okay. Eventually, if you go far enough, this will become a rectilinear motion. Right? This one and hyperbolic orbits are open orbits. And the elliptical and circular orbits are closed orbits. Circular. Now, when is the velocity and the position vector in the same direction? If I say B has a k component and R has a k component, and ask you to tell me what kind of orbit it is, what are you going to tell me? What kind of orbit it is? It is practically a rectilinear orbit, alright? What does k mean? What is the ijk here? You know what ijk is? Ijk direction? Huh? What is the direction? Where is I, where is j, where is k? No idea?
Is itself a z direction.
Huh?
A is coming out of the board.
If you're talking about ijk, I is generally in this direction. Okay? They have to be. Okay. So if R and P have the same direction, what does that mean? Do you see R and B having the same direction for the circular orbit or for the elliptical orbit? It's impossible, right? Because for circular orbit, V is always perpendicular. But for your elliptical orbit, it's never parallel. It is always at an angle. But for a parabolic orbit, R and V can be in the same direction. So think about this. If you go far enough, let's say somewhere there, what would be your R direction? Think about here. R direction would be, you just join this point to this F, right? Even V would be in the same direction, almost the same direction, right? So that is a parabolic orbit. Last but not the least are hyperbolic orbits. this is a hyperbolic orbit. So what is the orbit here? Can you recognize the orbit? No? It's one on the left and the right. The real body would do something like this. So this is where the central body is. Okay? F. Do you see this F? Orbiting body will do this. Okay? And will come back here. Okay? The orbiting body go here. It will go somewhere. Okay? Come back here. This is the hyperbolic body. It's like a comet. Yes.
Wait a second. It actually comes back on the other side.
It actually, yes, it comes back. So this is the power of Newton's laws. Okay. The reason you should appreciate the laws is, if Newton had not formulated his laws, he could have spent all our life on Earth, and we still couldn't have figured out why these planets are doing what they're doing. So Newton's laws, what did we say in the orbit equation? What did we say? That the orbit is a conic section, right? It could be any conic section. The conic section could be a circle, ellipse, parabola, or a hyperbola. So the orbit equation proved that an orbit could be a hyperbola. And when people actually did observations, they figured out, yes, it is actually doing it. So very, very good, very, very intriguing. Now, this is your RP. This is your RA. Here, one of the things you should notice, A is negative. The semi-major axis is negative. And E, centricity, will give you that. What are asymptotes? You know what asymptotes are?
Lines that get very close to that.
Right. So this orbit follows this orbit will never actually touch this. This is the center of the conic section. Okay? If you draw two asymptotes with this angle theta, right, the orbit is going to get very close to this asymptote, but never going to touch it. So you can precisely trace the trajectory of an orbit. You can actually draw very precisely the trajectory of an orbit. What you do is start with the center. You figure out what this angle theta infinity is. You would draw two asymptotes. Your orbit would be very close to that asymptote. Yes. Yes, ma'am.
I'm still not understanding how okay, if an object's going on the orbital path and it's right side, it goes down, it keeps going.
Mm-hmm.
How does it get back on the other side? How exactly does it get on the other side? Is it a 3D thing where
I'll let you figure it out. Why don't you read it up and tell us how it does that? But I can tell you for sure it does that, because we have done observations.
Where's the origin?
See, these don't have an origin. The thing with space is, you still don't know where the origin is, right?
These are not the original position either.
It's not. What do you mean by original position?
The initial starting point before it goes to orbit.
we haven't put any artificial bodies in a hyperbolic orbit, right? Natural bodies, we just don't know what started the whole thing. We're still trying to figure out. So the initial, very, very original position you're talking about, none of us know that, right? If you're talking about artificial bodies, wherever, if you were to put something in a hyperbolic orbit, wherever you fire your thrusters, that would be your starting position. Okay? So you get into, obviously you would not get into such an orbit directly. You would try to always go into a parking orbit. The reason you do that is, if you want to accelerate, you want to first get into a good speed. You just don't want to accelerate to that point and lose a lot of energy. So what you do is you go into a parking orbit, be there for some time, and then fire your thrusters to go into something like this or something like a parabolic. So that time your initial position would be wherever you fire. So you will be asked questions about these different types of orbits. We have done quite a few derivations in this. Last class we looked at a few derivations. The one derivation which I have not done is so that the energy of an orbit you need to show that energy is dependent only on size and not the shape. This today will conclude with chapter 2, but I want you guys to go through this derivation yourselves, and this will be definitely a question in your exam. Okay. When do you want your first exam? So when do you want your first exam? Next Wednesday? You want it in a week? No. I can give it to you. No.
Okay, fine.
Where's your real question is, when are we going to get the homework done?
The real question is, when do you take a look at the homework? When are you going to take a look at the homework?
Well, just as a point in general, sir, we want to get feedback from work that we've done on the topic before we're...
I understand. See, I'm doing all my part and more.
Okay.
To get you the feedback. No professor will be doing this. So, try to utilize the resources being given to you. I'm tracking what you guys are doing online, and I can bring it up and show you what you guys are doing. Okay? So, and I can present those results for each one of you. Now, unless you put in the effort, you cannot expect me to. I cannot be running. You'll be like this. If I start running, if I go for too much too ahead of time, okay, you'll never be able to catch up. So, yes, sir.
Alright. But you haven't necessarily, after Transformers on Wednesday, we would probably did that.
Turn it on Wednesday. I'll give it to you next week, the week's time.
So then we should have the test. We can complete it then.
When is your midterm?
Oh, good question.
Thursday, Thursday. 15 to 16.
October?
So
We can have 2 weeks from Wednesday. 2 weeks from this Wednesday.
that is you. This sounds hard.
Or 2 weeks, 2 weeks from today.
Okay.
I think that's a good.
Monday.
Yeah. Huh? Monday, yes. Assignments. How many of you have tried it or even looked at it? Huh? Have you started working on it? Hmm? So when are you going to, if you're confused, when are you going to talk to me then? We have one student. Huh? On? I'm not able to hear you. Say that louder. Hmm? No, I'm not going to solve the. It's not going to. I'm not going to come here to solve it. Why are we meeting Tuesday?
I thought we had extra review.
Extra review day would be after you're done your homework. So it will not be done by Tuesday. Submission. There is something called office hours, right? Huh? So you want to